So our next talk is also one of the TIP technologies. This one is cast aluminum forming austenitic stainless steel for high temperature and corrosive environments. And our speaker has been kind enough to allow me to introduce him as Morale.
Good afternoon, ladies and gentlemen. While no, it's a very long title. I'm going to explain every one of those words in that title. So before I start, I have...
Welcome to GoToWebinar, web events made easy. Please enter your access code followed by the pound or hash sign.
So what I'm going to talk to you about is what we, materials that probably, would find everyday use. Everyday you
to enable audio control, please enter your audio pin followed by the pound or hash sign.
If you think about it, what happens in these high temperature environments where there's water vapor, for example, or steam? What happens on materials that are used in very harsh, high temperature environmental conditions? So here's an example of actually cast AFA alloy, which is our cast alumina forming alloy. And here's actually a cast iron that's actually used in exhaust manifolds. And the reason why this example is up there is because water vapor is also a very harsh environment in many circumstances. That's what your corroded iron corrodes. Pipe outside, it corrodes. And so if you look at, for example, this is the cast iron, if you're familiar with the exhaust manifold, it's a high SIPO cast iron. And this is actually, of course, we try to test in simulated environmental conditions in the lab. But we also have experimentally tested. We also do follow-on tests in actually exhaust manifolds if somebody is willing to make it. So if you look at this cast iron, you can see how pitted it is. It's actually been exposed to 800 degrees centigrade for 5,000 hours. In 10% water vapor environment. It's a typical combustion, for example, if you look at that. And similar conditions for the cast alumina forming alloy, you can see that, of course, the surface is not pristine, but it's much less pitted and much less corroded. So this is exactly what we are looking for. Alloys that don't corrode significantly in high temperature, harsh environments. So how do we do this? And that's the first alumina forming capability. And what we do is, if you're familiar with the common alloys, for example, typically they are strengthened. I mean, they protected at very high temperature by chromium, which is Cr2O3. The problem with chromium is that it's actually reasonably fast growing. It grows, as you can see. Here's a component that has been exposed to 800 degrees C in air for 5,000 hours, and you can see how thick the oxide has actually become. Thick is not good, actually. So when I was coming to myself, I said, I wish I had a thicker coat. This is like a thinsulate, for example. What you have here is an alumina forming alloy, which forms a relatively thin oxide, but is still very protective. And the advantage of being
Welcome to GoToWebinar, web event.
For example, you have thermal expansion coefficient mismatches, and you take it to a high temperature, you bring it down, the thermal expansion coefficient mismatches, the oxide falls off, and now you are exposing more.
To enable audio control, please enter your audio pin followed by the pound or hash sign. If you do not have a pin, just press pound or hash.
That gives it a very tough adherent oxide layer that protects it in high temperature exposures. So the second thing, of course, in the title is cast, and of course, many people here may be familiar with castings. And so you near net shape, you make these in near net shape. You form the components in near net shape to form. And so what examples, of course, these are some industrial examples where you have a furnace row where these rows actually move plates of steel. They're exposed to air, which is again corrosive in many instances at high temperatures because of the oxygen. And of course, they're exposed to high temperatures, 800, 900, and so on. So you need those capabilities. Tough oxide scale, need the high temperature. There's another component, there's another part of it which I haven't talked about it yet. But here, for example, heat exchanger tubes. These are chemical processing, for example, chemical processing. They need resistance to water vapor, for example, and maybe even sulfur and more harmful species. And of course, your own exhaust manifold. I mean, it actually, if you think about it, the exhaust manifold is actually exposed to a lot of components in the fuel. And so that actually is also belongs to this harsh environment, as you will see, as I'll show you why it's moving more and more into harsher environments. And so these are, in addition to two things that I told you, the corrosive environment and high temperature is also subject to stresses. thermal expansion mismatch stresses, high pressure fluid going through, and so on. So this is what makes the problem really complicated. And our solution is, of course, the alumina-forming austenitic alloys. So why is this? And what are the opportunities that present itself? I gave you two examples. One of the rolls, for example, and the other one on the cast exhaust manifold. We'd like to think of this as, they're related, but they're kind of different applications. The cast alumina-forming austenitic stainless steels, of course, they form chromium, the thick layer that I showed you, but it's still protective, but they have a finite life, for example. And those are typically the HK, what they call the cast austenitics, the HK and HP, for example. And then the cast irons, of course, are used in exhaust manifolds. They're cheap and they're easy to make. And for most purposes, they solve today's problems. So what happens? Why is the scenario changing? Why should you may ask, why do you have to think about a new material today? Why can't I just do what do I have with what do I have? And there are two reasons. One is everybody's trying to push their equipment harder. They want to run for longer periods of time, push temperatures, get better efficiency, reduce the cost of fuel, and so on. So people are trying to constantly push environmental conditions. Well, temperature, 50 degrees centigrade in temperature isn't that big, unless you're a material science and you want to make that thing last. So most people say, I'm just increasing temperature by 10 degrees, 20 degrees. It's actually you're operating on the edge in many cases. So the other example is higher exhaust gas temperatures. As many of you may be aware, there is a push from CAPA standards to go to higher fuel efficiency. In fact, 2016 is 34.1 for light-duty vehicles. It's going to be pushed to 54.5 miles per gallon in 2025. What a lot of people are coming and talking to us saying, we are trying to keep the heat in the exhaust, for example. How do I, so they can get it through after the exhaust treatment and things like improve, keep your efficiency high, yet keep your particulate levels low, for example. Diesel engine manufacturers come and talk to us. We have automotive manufacturers coming and talking to us and saying, how can I give me what material you have for higher temperature exhaust. And cast irons, as I showed you, at 800C was really pitted. And right now, the reason why it still works is you're not at 800C. So people are trying to push it to 800C, for example, 700, 800C, and so on. And so things will start falling apart. And we have, in fact, we do work with some of the diesel engine manufacturers that are, they're very interested in technologies that can work good at the, higher temperatures. And so this is where we are. In terms of technology, we actually have an issued patent, and we also have a patent that's pending. And we actually also had an industrial scale heat. I showed you those tubes, long tubes. We had actually one of our industrial partners make one of those tubes. And we know that we can make it in that form. And so it's actually gone away from being just a pure lab scale exercise to actually going closer to an industrially viable process, for example. So going back to this properties. So I told you that there are three things: temperature, resistance to corrosion, and strength. What we talk about typically is what is creep strength. You have a material that's at a high temperature, you have it stressed at a certain level, and it will start extending or it will start increasing. It's essentially what we refer to as creep. It's slightly different from the strength as a yield strength, for example. So here on the left, I'm showing you the mass gain as a function of time, exposure time, of these alloys, of 2-3 alloys. These chromophores are here. There's actually, they keep increasing, they actually lose mass. And the reason why they lose mass is, if you remember, I told you that they fall off. They fall off. So the chromium oxide actually grows to a certain thickness and then fall off. And so it's no longer protecting the material. But here are the alumina-forming alloys. They're very adherent. There's not much growth in the layer, and it's very protective. And here on the right-hand side, I'm showing you what we also refer to as creep life. So you let a material sit at high temperature, and you load it, and you keep seeing how long it takes for it to fail, given that load. And so as you can see, the HK is actually one of the commercially available alloys, and we actually beat this significantly under these test conditions. We do have restrictions on temperature. I think I did kind of point out this 900, 950C is where we are very comfortable. That's the kind of maximum temperature we are comfortable right now to do these kind of tests. These tests actually are done at 750C. So where do we see the applications? We kind of like to think about two broad areas. One is combustion related, where you have water vapor, for example, and the other is actually just in air, even in air for high temperature. So industrial process, for example, I gave you examples of furnace rolls and reformer tubes of what you saw there. We are talking to people like ArcelorMittal who are who make these they make steel, and so they are interested in using these alloys in high temperatures, maybe around 900, 950 in air, even for example. But their biggest advantage is the alumina forming capability, and it doesn't score that. The surface quality of the steel plates is much better maintained if you have alumina scale than a chromia scale. We're also talking to people like liquid gas manufacturers, saying, they are interested in the alumina forming capability again, and in high oxygen environments. Of course, the other spectrum is combustion environments that exhaust manifold. I gave you an example, and there are other examples where you may find, for example, where you want to use in a combustion environment, you found that your existing alloys are not working, for example. And so we're also talking to diesel engine manufacturers. We're actively working with them, and so there's a lot of interest in these alloys. So how do we fit in with respect to many of the? I just showed you 3 properties. I didn't have a whole lot of time to explain all the others, but if you're making a component, you want to be able to make sure that you can weld it. And there are many others that make it a success industrially and commercially than just these properties. And so we try to capture some of these things in this table here. I'm sorry, it's a very busy table. But the biggest thing that you can see, the green signal, the green thing, so the oxidation resistance, the creep resistance, of course, is castable. I showed an example. Although we've not made an exhaust manifold, we allow for somebody to try it, to make it. And we are also talking to people like Cummins to see if they're willing to work with us. And one thing is of the cost. Of course, we are trying to bridge multiple technologies, so we cannot compete with cast iron on cost. So somebody who is interested in an exhaust manifold is not going to take this alloy because it's cheap. They're going to take it because it's the only way they can get to the temperature they want to go. So that's where in terms of these rolls and the heat exchanger tubes, we are very cost competitive, but then we have the advantage of better properties, so creep and oxidation resistance. So, when you have these multiple technologies, I just don't want to say, we are cost competitive with everything. But as always, the first adopters will be the ones that absolutely need the material. And we think that it's going to come in multiple areas. So, okay, the last thing that we do want to show is what is market potential. And market potential, again, I've just tried to capture 2 broad areas again. The stainless steel is very widely used in industrial processing environment, and even if you were to capture a very small portion of the market, it would be tens to hundreds of millions, small hundreds of millions of dollars, And of course, this is very approximate. And I was really surprised. The automotive exhaust system market is $33 billion. And this is where I got that from. It's one of these market surveys. And again, there is a lot of interest from companies because they feel that their existing alloys are going to be stretched in performance, particularly the cast irons. When 2025 comes, or within the next 10 years, in fact, even in the shorter time scale, they think that these alloys will be needed. And with that, I'd like to conclude my presentations. I'd be happy to answer any questions you may have. Thank you very much.
This material work as coating or as plant material?
We haven't tried it, but it could. Yes. We have made powder, so I guess we could definitely try to make it cool. Yes.
So could it be sintered as well?
Yes. Yes. Since we made powder, then yeah. And we have also made weld wire. So I think so those. Yes. That's a very good question. So we'll be willing to try it. And I think, as Mike pointed out, we have this project that we have funded to do for the first year. And so if there is really strong interest, that may be something that we could explore during this period of a year or so. 7 months, something like June, I guess. I think my math is off. This is more than 7 months.
Does this coating, how does it affect the electrical properties? You mentioned welding with it. Were there any changes, anything that would be accounted for there? Did you weld at your voltage?
I don't know the details of the weldability. You have anything? You have the details of the weld, exactly what process they welded this? yeah, is there some specific?
Did it change the electrical properties of the metal as compared to the chromium?
I don't think that's going to be an issue. Because I mean, essentially, all we're looking for is melting and resolidifying. If it's a solid state melting process, maybe it's a different story. But I'm not sure if that's going to be an issue. If it's a thick kind of GTAW, is that what you're thinking about?
I was talking in terms of resistance and.
Resistance welding. We haven't tried the resistance.
Not welding, sir. But say you were to make this into a wire.
We made it into wire. No, I don't think we have explored that, but that's a good point. Yes, sir.
Okay, so the base material, what's the base material?
This is the base. This is I don't know if I made it. It's actually a structurally integrated material. So it's actually solid material. So it actually forms the coating with the chemicals in the elements inside the material.
But it's something that's alloy.
It's an alloy, yes.
So what is it?
It's iron, nickel, chrome.
It's an iron.
Yes. Yeah, I mean, that's how we can stay cost competitive. Absolutely.
So can you talk a little bit about the infrastructure that would be needed if somebody were to try to begin?
We actually have been thinking a little bit about that. I mean, one of the things, of course, having any of these people interested in using all these aspects, who's going to make it for me, And so having the supply chain is a very critical part of getting acceptance in the market. And so if today somebody were to make it for us, we could have definitely people testing it. That's for sure. And so, we were thinking about it. I mean, we have seen, for example, $a few million is what it would take to actually set up the electrical furnaces and, the furnaces and casting facility, for example. But I think, I've been looking at some of these, periodicals that we do get in terms of supply chain. I mean, there are lots of these casting foundries going up even as we speak, because I think a lot of the offshore manufacturing is coming back, and the people that are opening up, foundries. So that's yes. I think the short answer to your question is $a few million at least, I would think. But I see numbers going from 5 million, those are typically expansion capabilities, but I think still probably would be in that ballpark.
Let's thank Ravi again.